This is the model that I put together to simulate the the micromodel in the Oostrom paper. This is an idealized version. It uses the same pore structure, but it's somewhat smaller of a region than the overall model that's described in the Oostrom paper. The model, let's just go through the model builder over here and take a look first at the parameters. There are three parameters, and these are all used in building the geometry of the micromodel. There are no definitions, so we can just skip over that part. The geometry is takes a little bit of finesse here, and it's pretty straightforward though once you get the knack of it. So we'll start here with the circle. This will be one of these solid grains, and so if I build it, you can see that solid grain right there. And one of the important things to see is that I'm using this parameter, large rad, the radius of this large grain, which I've entered here as a global parameter. So there's the large rad. It's 0.003 divided by 2. 0.003 is the diameter of the grain. That was from the paper. And so with that parameter, I've generated this geometric entity. And now I need to make a bunch of these. So I use this array copy, and that's right here under transform array. And so I put that in, I select this circle at C1, and then I'm going to make a 5 by 4 array, and each one of these elements in the array will be displaced relative to the other one by this amount along X, and as it turns out this same amount along Y. These can be different. These can also be functions, so you can get quite creative with these things. Well, let me say I think they can be functions. I'm not sure that I've actually tried that, but for sure they can be different spacing in X and Y. And in this case, they're constants, but they're constants that depend on these parameters that I've entered, the large radius parameter and the grain spacing. So if I do this, I get an array that looks like that. This is a 5 by 4 array, and the spacing from there to there is given by that expression. Now what I need to do is fill in and put large grains right here. So I'll do that by taking that grain, which is the 1 by 1 position in this array, and copying it and pasting it at displacement of X that amount and Y that amount. So I'm displacing it by 1 radius, particle radius, and 1/2 of the grain spacing. And when I do that, I get that. So I've got this grain and I need to copy it into an array. So I use the same array function that I used there, and then as it turns out, I'm going to copy this into a 5 by 4 just like I did for this one. So I just selected this array function and then used duplicate, and I got that array copy. And so I build select and I get those points. And now I need to go and do the small grain. So it'll be a small circle with that radius, and the location will be at Y equals 0 and X equals the large radius plus 1/2 of the grain spacing, which is there's 0, 0, there's the large radius, and 1/2 of the grain spacing is right there. So I get that circle right there, and then I need to use this same array copy function, and I do that and get the grains right there. And so we're going to repeat that. I'm going to copy this small grain to there using these displacements, and then I have to go and do another array copy, and I get that. So that then is my the grain arrangement of the micromodel. And the final step here is to add in this rectangle. This is the region that I'm going to simulate. This is where the flow will occur. This is not really an active region, so in this particular case I'm going to go and highlight those, select them, and then delete them with this delete entity function, and that's also obtained as one of the geometry. So there's no materials used here. The physics is laminar flow, and that I got here. If I went to add physics, and it's under fluid flow, single phase flow, laminar flow. So this is version 4.4 of Comsol, and if you're using a different version, this laminar flow may be in a different location, but this is the one you want, and I'll show you how to tell that you've got the right thing. The equation here, what it did was open up the equation, and you can check and see that you've got the Navier-Stokes equation. This is stationary, so there are no functions of time. We've got the convective acceleration here. There's the pressure, so this is a pressure gradient, and then the divergence of these strains. This is the viscous stress term here, and then the body force. This is the momentum, or this is momentum, and then this is mass conservation. So that's the equation that we want, and we want to have it be incompressible, and there's no turbulence model type because this is a very slow flow. So the fluid properties, actually let me show you one thing that's really important. So when you first put this laminar flow physics in, then let me close that. Then probably what it's going to want to do is select all of these different geometric entities, but you don't want to do that. You just want to select the pore space. So right here you want to, let's go and erase all of that. So all I really care about is that stuff. That's the pore space. So I think I can probably just use that. I'm not quite sure. There were a couple of other entities in there, but what you don't want to do, you don't want to have that grain selected, for example, because that's just that grain. You're just simulating the flow through the pore space, and that grain is not part of the pore space, and so that's not part of the problem. So you don't select it, and that's the reason why you can have these pieces of the grain here. You can also have some other grains outside of this region, and so long as you haven't selected them, they won't be part of the calculations. So the fluid properties are just the density and the viscosity of water, and the boundary conditions for the wall are no slip. This is the default. I also use the default initial values, and then we've got the inlet and outlet boundary conditions, and in this case I specified the pressure on the inlet and the pressure on the outlet. The pressure on the inlet is 1 Pascal, and the pressure on the outlet is 0 Pascal. So I selected these two edges right here for the outlet. Now the mesh that I used is important because the default mesh for this problem doesn't really work too well, and let me show you why that is. I'm gonna go and turn this back on and rebuild this. Here's what the mesh looks like. This is what the default mesh looks like here. There you go. So it's a triangular mesh and it gets a little bit finer near these grains, and so that's okay. This would work fairly well for some problems, but for fluid flow problems we have no slip along this boundary. So there is a boundary layer right along the contact between the fluid and the solid, and so there's a lot that happens there, and this mesh just doesn't resolve the shears that are going on along the boundaries very well. So instead of using this mesh, we'll disable it and we'll use this boundary layer mesh, it's called, and that's available right there. So if you select that, then you build it and you get a mesh that still has these triangular elements in the body of the pores, but if you zoom in, you can see that there are these very small, very thin elements right close to the boundary with the pore, with the solid grain. So you can see that's what this boundary layer mesh creates. Here are the default settings. You can fill around with those, but this works pretty well. So I would recommend doing this for all of these fluid flow problems. It's a stationary study, and we're really just interested in the steady state flow and pressure distribution. So if we run this, you can see that it really runs quite quickly. And here are the outputs, the velocities and the pressure and pressure gradient. And I showed you these in the PowerPoint before we started the model. So we don't really need to go through these in detail. I should point out, I guess, that I used a filled contour here. Let's take a look at the pressure. So this is the pressure distribution, and these are filled contours. So I put in, I made a contour plot, and the default is lines, but I've filled in the lines right there to get this solid. And what you get when you do this is a plot that has solid colors that abruptly transition at a contour line. This is opposed to the default color flood where the colors grade from one to another. And so this kind of contour plot is, I like the look of this for some applications. So I wanted to show it to you as an example. Here, this is showing the streamlines. That's put in quite straightforward to put in streamlines, just add it here. And then I guess there's one last thing. In order to determine the effective hydraulic conductivity of this porous material, I need to know what the flow through this material is. And so I do that by going over here, derive values, and there are a variety of options here. I'm going to select the average over the line. And so I selected that, and then I selected, let's just erase this, and we'll select that and that. And I'm gonna take the average u, which is the velocity in the x direction, and so I set that up. And let me see. Okay, this is all default, and I said go. I'm going to go, and if I click that X, I clear out all of these previous calculations, and then I click evaluate, and that is then the average velocity over in the X direction over this line. And so I can use that with the pressure gradient in order to calculate what the effective hydraulic conductivity would be of this material.